of circuits in this diode. So at the beginning, something very simple. We have a very simple circuit with one diode and one resistor. And we have seen in the lecture a couple of have any other lectures in this room? Do you know the room?
I think here, there's a small one.
No, I'm just looking for the pen.
Okay, no.
Professor, should I bring from the library
I'm not sure if it's the same system.
some markers so you can write on the board?
I have markers,
Okay.
but I prefer actually working there so I can just
Okay.
save it later on and upload it. I have enough markers.
Maybe try this one. See if it works.
Oh my gosh.
I'm not sure if it's working, but it sounds not very smooth. I'm not going. I don't like to make it. I'm just going to try to check if I can get one from the other room.
চলো আমরা একটা চেক করি
আপনাদের জন্য তুমি আছে আমার কাছে টাকা
মরে দাও
আসতেছেন কেন আপনি বলছেন আমি চলে এর জন্য আসছি শয়তান
এবার একটা উপকার করেন বাইন্দা দেন ওই ওয়াও থ্যাংক ইউ আল্লাহ তোর জন্য
Okay, good. Again, so this is a very simple diode circuit, and we need to calculate the circulating current with the three approximations. So probably before we start doing this, what are the three models or the three approximation models we have seen for the diode? How can we calculate the diode? So the first, I would say, most easiest one to think about is the standard mathematical model. This Shockley equation with a lot of complicated mathematics behind. We will be never using in class. So instead of that, we decided to model the diode, and based on that we talked about different calculations, different approximation models, and we learned the three most important ones out of them. So what is the most easiest one?
Ideal diode is this one?
What is ideal?
On, off.
Exactly. We have two possibilities for a diode to be like a switch, which is off or on. This is off, and this is on. This is the ideal model. What is the second model? Yes.
Constant voltage drop.
Piecewise voltage drop, which is the easier one. If we think after, the ideal is like really ideal. We either have current or we don't have current. We don't think about voltage, resistance, and so on. So what is the next possible approximation? Piecewise or voltage drop? By the way, voltage drop is known in a lot of books as part or as a model out of the piecewise model. So voltage drop, as we just call it, constant voltage drop. We just extend our switch model to kind of constant voltage drop. This is off or closed switch. So how big is this constant voltage?
0.7 volts.
For silicon, exactly. Be very careful in the exam. If it's silicon or germanium or something else, LED is going to be totally different. But in our case, we are working with silicon. That's why 0.7. This is the constant voltage drop model. And the latest one, piecewise. What is piecewise exactly?
Having a resistance.
Exactly. We have a voltage drop, which is a 0.7, and in addition we have a small resistance for the diode itself. This is a piecewise. One, so we have the two options. We have our switch, we have voltage, and we have our, let's call it up. This is off, and on the other side we have the on, where switch is closed, and we have our on.
So is the resistance used in this model the same as the bulk resistance?
No, this is the internal resistance of the diode itself. Usually few ohms, very small resistance. That's why we can just model it as being zero, for example, with the ideal model or with the constant voltage drop. It's really small if you compare it with the 1 kilo, for example, in this or 2 kilo. Good. Those are the three models. In order to solve this mini circuit, we have to decide at the beginning, for example, how the current is flowing. In our diode, we have this side is the positive side, is the cathode, the anode, sorry, this is the cathode, this is our voltage. And how the current is flowing inside the diode from the anode to the cathode or the other way around. Usually on the anode side, on the positive side, we have the P side of the junction, a lot of holes moving from the other side, from the P side to the N side. Electrons are coming from the right side to the left side. That means conventional current is the other way around. So let's just do it now for the ideal, model, we have the circuit with our voltage. Now if we just take a look to so is our diode in this case in off mode or on mode, and why?
On.
In ideal, we know we don't have a lot of possibilities for one diode. It's either on or off. What can we do if we have multiple diodes? The diodes, 2 diodes, 3 diodes, 4 diodes?
2 to the power n.
2 to the power of n possibilities, and just try. For example, we start with on and check if it's correct or not. In this case, it's obvious because the positive side, the anode side, is connected to the positive side of the supply voltage, and the negative side is connected to the negative side. That's why it's easy to do it that way. That's why I'm going to say this is the diode. Actually, here we have our resistance, volt and 2 kilo ohm. Very simple equation. This is our ID. Ohm's law. V is equal to ID multiplied by our resistor. That means our current is V divided by R, which is 12 volt divided by 2 kilo ohm. Volt divided by ohm is ampere, and 1K is milliampere. That's why we have 6 milliampere for this model. In this case, we have for the constant drop voltage model, we have 0.7, and again we will have the same story. If we apply the TCL, TVL, and Ohm's law, we will get in this case that 12 volt is equal to 0.7 volt. This is the constant voltage drop on the diode, plus ID multiplied by 2 kilo ohm. That means that ID is 12 minus 0.7 divided by 2 kilo. Which is 5.65. Now you can already see like a very short comparison. We have 6 ampere and 5.65 milliampere. It's actually, when we are doing something very simple, we are working with our Arduino or whatever, it's quite better to take the ideal model because it's not really this big difference between all of them. And let me take this place to just simulate the latest one, which is the piecewise model, 12 volt again. We have now not only our diode, which is now shorted because on, we have our 0.7 volt, and we have now the simple model of the diode. Very important, all of this is the diode. The resistance, the constant voltage strobe, and the switch. And then if we just continue, we have then in addition this 2 kilo ohm load resistor. Now again TCL, TVL, we have the same story. 12 volt is equal to 0.7 on this side. Very important, now we have the ID flowing through the load resistor, but also the diode resistor. That's why it's plus ID multiplied by RD plus R. This is actually the difference we have now.
كويس هو اسلوب ده هناك شو
Plus ID multiplied by R. And here we can get the ID is 12 minus 0.7, now divided by 2K. And depending on the question, we have 10 ohm, right? For our stuff. Take extend ohm. Which is equal to 5.62 milliamp. It's even lower, something around 1% between the constant drop voltage model and the piecewise model. And this is how you always work with the diodes. Good morning. Of course, this first exercise is just to get to know the models in the exam or in the homework or whatever later on you will get immediately given. This is the circuit. Treat the diodes to be ideal, use the voltage drop model, use the piecewise model, whatever. And it's always given in the exercise what model to select. Just in case, in any of the situation, you don't have any suggestions what to use, you can just select the model you would like to take and take it. But usually, especially in the exam, I'm giving you exactly what I want to see. Ideal model, voltage drop model, and piecewise model. Any questions so far?
So what's up in the, for the real world, the third one would be the most appropriate.
Exactly. This is exactly. This is the move. Actually, if you would like to have exact numbers, probably you can try this at home. Just take the Shockley equation, the exponential function, and put the numbers, and then you will see that it's going to be more detailed, 5.61235. But the piecewise model is the most realistic model from those three. But if you would like to take really the real numbers, you need to work with the mathematical model, which is the Shockley equation.
So we need to draw the graph and we see where does the graph.
Exactly,
Okay.
exactly. Linear model, or just really calculate with the exponential function.
Okay. And Professor, one more question. What about the small signal analysis? We don't include here for the approximation? Or
Good question. I think small signal will be doing in the next exercise. So what was exactly the difference between the small signal analysis and the standard models we are treating right now?
We have an AC signal in the power source.
Exactly. Small signals is actually when you have part of your supply is AC. In this case, we are dealing mainly with DC voltage. That's why we are using the approximation model. Next time, I'm not sure if we are going to do this for the diodes, but especially later on when we start with the transistors, we'll be bothering a lot with the small signal analysis and all of this stuff. But now for DC, it's ideal voltage drop or piecewise model. Of course, you can use this load line graphical analysis, but this is not really suitable for calculation. Good. Any other questions? Okay, next one. What will happen if we now have this circuit? Exactly the same circuit. What is different right now? The diode is reversed, or actually it's at least on the other side. Here we have our plus, and here we have our minus, our anode and cathode. In this situation, what is the mode of the diode?
Reverse bias.
It's reverse bias because the N side, which is the electron side, let's say, is connected to the positive terminal. They are going to be attracted. The holes are going to be attracted from the other side. It's open. That means we have something like this. So what about the circulating current in this area?
0.
It's open, no current. What about the resistor voltage?
It's also 0 because there is no current and it is
Fixed current voltage.
Exactly. And what is about the diode voltage?
same is the supply voltage.
Something like this. And then we have that the voltage of the diode is equal minus this. Which is the breakdown voltage, zero ampere, breakdown voltage, everything and so on. It's something very, very simple. And this is how you can actually later on model circuits with multiple diodes. But we'll be doing a couple of them later on, and we'll be discussing them in the next one. So the main message out of the first exercise is to understand the three models and to be able to apply them. Very simple exercise in the beginning just to get them. Now let's move to the next one. Determine the circulating current for the circuit in the figure below. Also find the diode and resistor voltage. Assume power supply to be 9 volt. The diodes are silicon. R1 is 1 kilo ohm, R2 is 1. Probably the first question, did you just try at home to do something with the exercises? Did you prepare something? Okay. What should I do here?
So let's take constant voltage drop here. So let me 9 volt minus 1.4 divided by 3 50 ohms for the cycle current.
Why?
Because both of the diodes are in on position.
Exactly. This is the first thing we need to think about. We have multiple diodes, even before we define which model to take. Can we obviously find out from the direct first look, let's say, to the circuit, whether we have forward bias or reverse bias? Let's take diode number 1. We have the anode connected to the positive side, and we have on the second diode the cathode connected to the negative side, so it seems like both of them are able to be on. Then we can take them to be on, and then second we can define. In this case, it was really a mistake from my side. I didn't give you an assumption what it should be, but we can take the voltage drop model, why not? And we assume that since we have positive to positive, negative to negative, that D1 and D2, both of them are on. So how it's going to look like? We are going to have our voltage, which is 9 volts. We have our first one. Now the first switch is closed. Then we have our 0.7 volt because we decided to take the voltage drop model. Then we have our second resistor. R1 is 1 kilo. Here is 2 kilo. And the second one is again the same. Also, second switch is closed. And now we can just do the same analysis. And we are going to get the ID by the way, the first, so the same one for both of them. What is the voltage we have? We have 9 volt on this side. On the other side, we have 2 times 0.7 volt. That means 9 minus 0.7 minus 0.7 divided by the overall voltage, which is, resistance is 3K, which is then 7.6 divided by
2.533 million. 2.533 million.
So, was our assumption correct? Yes or no?
You should check it with all the voltage across the resistors and the voltage drop across the diode. And if they sum up to 9, then all the ratios are there.
Yes, but the most important information we got is that ID is 2.53. We have a current flow in there for both diodes, and that's why. But in this exercise, it's really obvious that it's doing that. In any case, if we would have assumed something different, we will see that the voltage drop is higher. That's why it's not correct. But we will be doing this later on in some other exercises. Okay, good.
Sorry, can you repeat, how do we know this model, this is a correct assumption? I mean, it's obvious, but what did you?
Now we have ID is 2.53. You have current flowing through the first diode. We assumed actually that we have current. If you get something like minus 2.53,
Okay, yeah.
it's going to be
Okay.
the wrong assumption. Yes.
How do you decide what is used?
In this case, just as I mentioned at the beginning, I actually just forgot to say use this and this model. You can take whatever you like. If you would have taken the ideal model in here, you just remove the 0.7 and 0.7, it's going to be 3 amperes. So if you just decide to take the piecewise model, you will have a small resistance in here, but since we don't have the internal resistance of our model, so we are not going to be able to do it. You can just assume 10 ohms or something like this, but probably I'm going to change this, the question, and add use voltage drop model to it.
So in the exam, you will just specify.
In the exam, you always get the what I would like to see. Just in case, I'm definitely sure in the exam I'm not going to forget that, you can just take the one you would like to. For example, usually, it depends also on the question you have. For example, the diodes are silicon. This information is only important if you are not taking ideal, right? So if you decide to take voltage drop model, it's fine, you can take a 0.7. If you decide to take the piecewise model, you will just recognize, okay, I still have a missing information, so I'm going to take the voltage option. But still, I'm definitely going to try to just say, take this one and use this one. Good. Same question. So we have the 10 volt in here. We have 1 kilo. And we need the source current and resistor voltage in this case. What's the first thing to do? What we discussed at the beginning?
See the tag is on or off.
Yes. Decide, see, guess, approximate, whatever you would like to call it. We have to make an assumption at the beginning. So is it, what do you think? Is it on or off? It's on, obvious, because we have the negative on the cathode, the positive more on the anode side, so it's going to look like this. So what is the current?
We need to first figure out the mesh type of mesh 1 and mesh 2.
Do we have to apply mesh?
I think so, but we have two meshes here, mesh 1 and mesh 2.
Here we have the current in here. Here we have our 9 volt. Here we have ID. 10 volt. And here we have also kind of current. So what is, how do we solve this?
So for the first mesh or first loop, it should be 9 volt minus 0.7 divided by 1K. And for the second loop, it should be 0.7 divided by 1K. And then we see which current is the larger one and subtract that out.
Would you like to do it?
Yeah, sure.
It's 10 volt, right? Not 9.
Yeah, then.
Oh, sorry, 10 volt.
Can I do it on the 5 volt?
You can take whatever you like, but you can also take this one, so we can just save everything later on. So just use, you don't have much place, but it should be actually enough.
থেভেনিন তো কমপ্লেক্স না তো ইজি এটা সমস্যা নাই তো একটা অ্যানালাইসিস করে আমি কিছু করতে পারবো হ্যাঁ এটা অনেক হার্ড কিছু নাই যদি থেভেনিন ইউজ করা কিছু না জাস্ট অ্যানালাইসিস দিয়ে বসে
What you are doing is actually quite perfect. But I would say, this is why I wanted to see what you are exactly doing. I would say you are doing definitely more than I'm asking about, or the question is asking about. The question is, determine the source current. This is the source, and you would like to have the current in here. So which actually almost done by you, right? So you have this, you can just take this mesh. So you would have 10 volt is equal to this voltage plus this voltage. And this voltage, you have the R, you can just determine the source current directly. You are doing the second mesh in order to calculate how much current you have here and how much you have current here. Okay? Great. Exactly. But usually, perfect, thank you, great. So usually what we should do actually is very, let's say very, I would say, simple. And this is again one very important point for the exam. Read the question and understand what is exactly required. What we need is the current of the source current, which is this input. We need this one. For that, we need, or we assumed that the diode is forward biased. So we have again this mesh stuff, KVL, KCL, and we will find out, it's again, it's 10, not 9. So we have the 10 volt is equal to this current we are looking for, multiplied by 1K plus 0.7. That means our current is equal to 10 volt minus 0.7 divided by 1K, which is, should be quite easy. 10 minus 0.7 is 9.3 milliamp. This is the main current here. Second one, resistor voltages, both of them. This one is quite easy, 9.3 multiplied by 1K. And the other one is actually the same as a diode because they have the first start and the first beginning. Here it's very, very clear that they are parallel. But usually in the exam and always in any circuit you see, sometimes they don't really look like they are parallel. Look always to the beginning and to the end. If they have the same beginning and the same end, that means they are parallel. Parallel means the same voltage drop. If we have 0.7 over the diode, that means we have 0.7 over the second one. This one is 0.7 volt, and this one is 9.3. 9.3 volt plus 0.7 is 10. Everything is quite fine. Feel free to take any pictures. I don't have any problem with that, but I'm going to upload exactly those slides next week, always 1 week later. Today I'm going to upload the slides from last time and this one and so on, so you have some time to just get busy with the exercises without having the solution directly in front of you. Okay, any questions so far?
Professor,
Yes.
for this one, because you use constant voltage drop, right?
Yes.
But we
Yes.
can also use like ideal so that the R2 is totally short.
স্টিফেন হ্যাংলের যদি এরকম হইতো
Exactly. That means we will have voltage drop over R2 is 0 because it's going to be shorted, and we will are going to have the complete 10 volt over R1, and the current, what about the current? The current is going to be 10 divided by 1K is going to be 10 milliampere. Again, something very perfect and very quite good for our simple working in the lab with microcontroller stuff and so on. 10 microamperes and 9.3 milliamperes is not really this big difference. Question is, I got yesterday a question from a student. Okay, we have seen the exercises I'm preparing, and even if they are so simple, I have problems with them. How many diodes are we going to have in the exam? 3 diodes, 4 diodes, because as you mentioned at the beginning, it's 2 to the power of p. That means if you have like 10 diodes, or let's say even if you have 4 diodes, you have 16 possibilities. Again and again and again, this is the first time I'm doing this lecture here in this university, so I didn't bother with exam questions before. I would say up to 3 diodes in a circuit should be relevant. So probably not really a circuit with like 10 different diodes, but I would say 2 diodes is probably fair enough, but 3 diodes you should also be able to deal with. And you will see it later on. The more exercise you have, the more ideas you will have how to find out the real guess before you start. So So for example, in the case before, we have seen directly both of them are on because they are connected in the right direction. Sometimes it's not really easy, you can just take a guess at the beginning and calculate. Good, let's move on. Source current, so very important. Source current, resistor voltages for the circuit, 1 and 2 ampere. Diode polarity is so we have here 1K. So what we should do with the diodes. This is the first thing we need to clarify before we think about any of the models.
D1 is on, D2 is off.
You're too close.
So D1 is on, Y is on. We just take a look and we can see almost directly that the cathode is connected to the negative terminal, the anode is connected to the positive terminal, so it should be on. And D2 is exactly the other way around. We can see that the negative terminal is connected to the cathode. So it means it should be reverse biased. So we can make an assumption D1 is on and D2 is off. So now we need to select which model to take. What do you think? What is going to be the appropriate solution in here?
Constant voltage drop.
Yeah, constant voltage.
Okay, any other ideas? Which one is going to be the better one? Ideal, yes. If I am mean, and I'm not mean, I would say, okay,